So I want you to imagine that you walk into a room and there is this massive whiteboard taking up the entire wall.
Oh, like a classic movie mathematician scene.
Right, exactly. And it is just absolutely covered edge to edge in the most intimidating, dense calculus you've ever seen. We're talking, Greek letters, squiggly integration symbols, little subscripts everywhere.
Just differential equations stretching from the ceiling all the way to the floor.
Yeah.
Yeah,
And at first glance, this just looks like, well, a whiteboard full of intimidating ivory tower math that honestly has nothing to do with the real world.
right. It feels completely disconnected.
But today, our mission for this deep dive into these sources is to show you that this whiteboard isn't just abstract math. It's actually about the philosophy of time, the nature of randomness, and really how human beings manage to build these mathematical cages to trap the unpredictable chaos of the financial markets.
And, the craziest part about that cage, it only works if we assume time behaves like a liquid rather than, a ticking clock.
A liquid. Okay, yeah, we're definitely going to get into that.
Oh, we have to. Because to understand how Wall Street prices literally trillions of dollars in derivatives, we are going to journey from the microscopic, jagged, entirely random movements of a single stock all the way up to the macroscopic, smooth certainty of global option pricing.
Reading through these sources, it is a wild ride from absolute chaos to absolute order.
It really is.
So let's start at the very bottom of that whiteboard. The absolute foundation of everything we're looking at today begins with something called simple Brownian motion.
Right.
In the math, it's represented as a W with a little subscript T. To visualize what this actually is, picture a tiny pollen grain suspended in a drop of water.
Being constantly bombarded by microscopic water molecules from all sides.
Exactly. The botanist Robert Brown first observed this in the 1820s, and he couldn't figure out why the pollen was just jiggling around as if it were alive. But it wasn't alive, right? It was just experiencing pure, continuous physical randomness.
Right. And that physical observation is really the bedrock here. Simple Brownian motion is basically the atom of randomness in continuous mathematics. It's the core building block.
The atom of randomness, I like that.
But to move it from physics to finance, the sources often use the analogy of the drunkard's walk.
Right, the drunkard. Imagine a perfectly drunk person stumbling in a vast, flat, empty field. They take a step. Is it left? Is it right? Forward? Backward?
It is entirely unpredictable.
Completely. This is the purest form of continuous random noise. If we look at the properties outlined in our sources, this process has a mean of 0.
Meaning, on average, if you let this person stumble around for 100 years, their expected location is exactly where they started.
Right, they aren't trying to go anywhere. But the second property is what's really crucial here. The variance, basically how far they might theoretically spread out or drift from the origin, is exactly equal to the time that has passed, which is denoted just as $2.
Let's actually pause on that variance for a moment because it is essential to internalize.
Okay, lay it out.
The longer the drunkard walks, the wider the area in which you might find them. If you search for them after 1 minute, they're probably within a few feet. Right? But if you search for them after 10 hours, they could be miles away in literally any direction. The uncertainty grows linearly with time. But, and this is the kicker, as a foundation for a financial market, this model is completely inadequate.
Because it has no direction, right?
Precisely. It is a pure, unbiased diffusion.
Yeah.
If you're trying to model the price of a stock or, the broader economy, a completely unbiased wander just doesn't reflect the fundamental nature of capitalism.
Right, because stocks, generally speaking, are expected to grow over time. Investors demand a risk premium for parting with their capital.
Exactly. There's a time value to money. If you put money in an asset, you expect an upward trajectory over a long horizon. So, the mathematicians realized they had to upgrade simple Brownian motion to something called arithmetic Brownian motion, or ABM.
Okay, I'm looking at the equation for ABM right now. It's dgxt mu dt plus sigma dw tdo. To bring our drunk person back into the picture, ABM is like taking that exact same staggering individual, but instead of putting them in an empty field, you place them on a wide, moving airport walkway.
I love that analogy. It's perfect.
Right. There is still that random, unpredictable stagger from side to side. That's the sigma dwd part. The sigma is the volatility multiplier. It dictates how violently the person is staggering.
Right, the sheer chaos of it.
But then there's also an overall relentless forward directional drift. That's the moving walkway, the DTD part. So now you have a deterministic trend, the walkway, with pure randomness layered on top of it.
Exactly.
Now, reading through this initially, I hit a mental roadblock. If arithmetic Brownian motion gives us an underlying trend, which represents the expected growth of a company, and it gives us realistic, unpredictable volatility,
Yeah.
why isn't this the holy grail?
Right. Why look any further?
Yeah, why can't we just use this equation to model the absolute price of Apple or Microsoft? It seems to have all the necessary ingredients.
It definitely seems like the complete package at first glance. But if you attempt to use arithmetic Brownian motion to model absolute real-world stock prices, the model immediately crashes into two fatal structural flaws.
Okay, let's unpack those.
The first flaw violates the most basic legal and financial reality of modern markets, which is the principle of limited liability.
Oh, right. Let me try to break that down. If I buy 10 shares of a retail company and that company goes completely bankrupt, say they have terrible management and billions in debt, the worst thing that can happen to me is that my investment goes to zero.
Exactly.
The creditors cannot come to my house and take my car to pay off the company's debts.
Yeah.
My liability is strictly limited to the money I put in.
That is the legal reality.
Mm.
But arithmetic Brownian motion, it does not know what limited liability is. ABM is essentially a normal distribution, a bell curve that is steadily spreading out over time.
And bell curves have tails.
Right. Because it is a normal distribution, its tails stretch out into infinity in both directions. The drunk person on the moving walkway can eventually stagger so far to the left that they fall off the edge of the positive numbers entirely.
Wow.
Yeah, the model might spit out a prediction that your shares in that retail company will be worth -$50 next year.
Which is physically impossible in a stock market. You can't owe $50 a share just for holding a standard equity. So the model is generating completely fictional realities.
It generates absurdities. If your mathematical model says an asset can be worth less than zero, you cannot use it to price options or manage risk. You'd be pricing in events that can never actually happen.
That's a pretty massive flaw.
It is. But the second flaw of ABM is arguably even more problematic for day-to-day finance.
What's that?
Arithmetic Brownian motion completely ignores the reality of compound interest and proportional returns.
What do you mean by proportional returns, like percentages?
Exactly. ABM models absolute spatial movement. It models the actual dollar amount of the change. So the model treats a $10 drop in a stock exactly the same way, regardless of the stock's current price.
Oh, I see.
Let's say you have one stock trading at $1,000 and another stock trading at $11. To ABM, a -$10 random jump is mathematically identical for both.
But logically, those are two vastly different universes of pain. I mean, if my $1,000 stock drops $10, I barely notice. That's a 1% blip. I probably don't even open my brokerage app.
Right. It's nothing.
But if my $11 stock drops $10, the company has practically been wiped off the face of the earth. 90% of my wealth is incinerated.
And yet, arithmetic Brownian motion sees literally no difference between a 1% blip and a 90% wipeout. It lacks the self-awareness to know where it is currently standing. It only knows -10 steps.
So it's completely blind to scale. It sounds like ABM is useless then. Why even include it in the source material?
Well, it is entirely useless for modeling absolute stock prices.
Yeah.
However, mathematicians rarely throw a tool away completely.
True.
ABM is actually the perfect mathematical framework for modeling the log returns of an asset.
Log returns, meaning the percentage growth rate rather than the dollar price.
Exactly. Because think about a percentage growth rate. Can a growth rate be negative?
Yeah, a stock can grow at -5%.
Right. Can growth rates be additive over time? Yes. Continuous compounding works additively.
Yeah.
So ABM fails at modeling the price itself, but it succeeds beautifully as the engine for modeling the rate of return.
Okay, but to actually model the price itself, the mathematicians had to invent something new.
Right. They did.
And this brings us to the real hero of the first part of our sources, geometric Brownian motion, or GBM. To fix those fatal flaws, they made a remarkably simple tweak to the ABM equation.
It is elegant in its simplicity.
Right. Instead of dx2 we now have dxd dollars. And the new equation is dyt dxt plus sigma yt dwt. If you compare the two, all they did was multiply the drift term and the volatility term by y dollars, which represents the current price of the asset. It seems like, I don't know, a minor bookkeeping change. Just tossing the current price onto the right side of the equal sign.
It looks like a minor adjustment, sure, but mathematically it changes the entire universe the equation operates in.
How so?
By multiplying the drift and the noise by the current state, they introduced a property called scale invariance.
Okay, let's unpack scale invariance. What does that actually feel like in the market?
It mathematically enforces the idea that a 1% return behaves identically no matter how expensive the stock is. Let's go back to your $1,000 stock and your $11 stock.
Okay.
If the noise factor, the WTD, dictates a negative 1% random shock to the system, the GBM equation scales that shock. For the $1,000 stock, it calculates 1% of 1,000, resulting in a $10 drop.
Right.
For the $11 stock, it calculates 1% of 11, resulting in an 11-cent drop.
Oh, wow. So the volatility isn't an absolute sledgehammer anymore. The volatility shrinks or grows to fit the size of the company.
Exactly. The relative percentages are perfectly preserved. And because of this scale invariance, the first fatal flaw, the negative prices, is simultaneously cured.
Because it can't drop by more than 100%.
Well, structurally, the solution to the geometric Brownian motion differential equation involves an exponential function. And as you might remember from algebra, an exponential function with a real base never touches zero.
Right, it becomes an asymptote.
Yes, it can approach zero, it can get infinitesimally close, representing a company bleeding out over decades, but it can never mathematically cross over into negative territory.
The exponential function builds a physical wall at zero. It perfectly maps to the legal concept of limited liability. I just find it fascinating how a mathematical quirk can so perfectly encapsulate human corporate law.
It's beautiful when the math aligns with reality like that.
But as I read deeper into the source material on geometric Brownian motion, there is a theoretical assumption here that I think a lot of everyday investors are going to hate.
Oh, I know exactly what you're going to say.
It's the concept of the Markov property. The texts describe GBM as a memoryless process.
Yes, the Markov property is basically the philosophical battleground between quantitative mathematicians and traditional stock chartists.
Right.
To say a system is memoryless means that the future state of the system depends only on the current immediate state, and absolutely nothing else. The path it took to arrive at that current state is statistically void.
Okay, let me put this in real-world terms to see if I'm grasping how extreme this really is.
Go for it.
Suppose I have a biotech stock. It has been grinding upward for 5 straight years, a beautiful 45-degree angle on the chart rewarding everyone who held it. Today, it sits at $100. Now, suppose I have a second biotech stock. It was at $500 yesterday, but a massive scandal broke overnight, the CEO was arrested, and the stock completely imploded, plummeting down to $100 this morning.
Ouch.
Right. Both stocks are currently at exactly $100. The Markov property says the statistical probability of what happens to either of them tomorrow is identical.
Within the strict confines of the standard geometric Brownian motion model,
Yes.
they are identical.
That's insane.
It is counterintuitive for sure. The driving force, the WWD is pure independent white noise. Think of it as a fresh dice roll occurring every single millisecond.
Okay.
The current price at $100 is assumed to have completely absorbed every single piece of historical data. The 5 years of steady growth.
But
Priced in.
the CEO getting arrested yesterday.
Priced in. All of human history regarding that company is crystallized into that single digit. Therefore, the history is entirely irrelevant for predicting the statistical distribution of the next millisecond.
That is brutal. It completely invalidates the idea of momentum or trends relying on past price action. It basically tells anyone drawing support and resistance lines on a chart that they are looking at clouds and imagining shapes.
It aligns very closely with the efficient market hypothesis in economics.
Yeah.
The idea that you cannot beat the market based on historical public information because the current price is already the perfect equilibrium of all known info.
Right.
But the model goes even further to enforce stability. It is not only memoryless, the sources describe it as being time homogeneous.
Time homogeneous. I noticed that when I was looking at the coefficients in the equation, the millidollar for the drift and the sigma dollar for the volatility. They don't have a little teen attached to them. They're constant parameters.
That is the key. The parameters governing the mechanics of the assets movement do not contain the explicit variable of time, meaning the rules of the game do not care about the calendar. The statistical probability of how the stock might behave over a 3-day period is exactly the same, whether those 3 days start on a random Tuesday in 2026 or a Thursday in 2035.
It's just the duration that matters.
Exactly. The math only cares about the duration of the time step, the length of the interval, not the absolute date.
Okay, so mathematicians have constructed this incredibly elegant cage. Geometric Brownian motion respects the zero boundary, it scales with proportional returns, it ignores history, and it operates with constant rules regardless of the calendar date.
It's a masterpiece.
But this is where our deep dive takes a massive left turn. Mathematicians had this beautiful equation, but when they actually tried to do the math, when they tried to run calculus on these Brownian motion equations to figure out pricing and expected values, everything broke.
Completely fell apart.
The calculus invented by Isaac Newton and Gottfried Leibniz in the 17th century, the calculus taught in literally every high school and university on Earth, completely stopped working.
It was a full-blown crisis of mathematics. Classical calculus is built on the fundamental assumption of smoothness.
Smoothness.
Right. If you zoom in close enough to a curve in classical calculus, it eventually looks like a straight line. You can draw a tangent line to it, calculate the slope, and figure out the rate of change.
Which is the whole point of derivatives.
Exactly. But Brownian motion, driven by that random dw term, is a fractal.
Okay, I want to make sure I understand the physical nature of that fractal. If I look at a standard stock chart for a year, it's pretty jagged. If I zoom into a single day, it's still jagged. If I zoom into the 1-minute chart, it's just as spiky.
But if you had a microsecond chart, it would look identical. They're the definition of a continuous fractal. It has no breaks, you don't pick up your pencil to draw it, but it is infinitely spiky.
Infinitely spiky.
It is nowhere differentiable. Because it instantly zigzags at every microscopic point, you can never zoom in enough to find a smooth straight line. You can never draw a tangent.
So if there's no smooth line, Newton's calculus has nothing to grab onto. The traditional tools literally slide right off the equation.
Precisely. And this gridlock required one of the greatest intellectual leaps of the 20th century. During World War II, a Japanese mathematician named Kiyoshi Ito, working largely in isolation, realized that if you introduce continuous fractal randomness into a differential equation, you cannot use the old rules.
You need a new rule book.
You have to invent an entirely new branch of mathematics, and he did. We now call it Ito calculus.
And reading through the axioms of Ito calculus in our sources, there is one rule that stands out as the absolute linchpin of the whole system. It's this tiny, unassuming little substitution rule. dWtu equals dt dou.
The magic formula.
Right. Let me translate that from the math notation for you. It says the square of the purely random, unpredictable noise is exactly equal to the relentless, deterministic change in time.
That's wild, isn't it?
I have to be honest, when I first read this, my brain rejected it entirely. How can you take a completely unpredictable variable, basically a random dice roll, square it, and suddenly it transforms into the rigid, perfectly predictable ticking of a clock?
It sounds impossible.
That doesn't feel like mathematics. It feels like alchemy. Chaos squared equals time.
It is easily the most counterintuitive concept in quantitative finance, and yet it is the reason global markets function.
So how does it work?
To grasp how chaos becomes time, we have to discard how we think about macroscopic objects and descend down into the microscopic limit. We have to apply the law of large numbers to infinity.
Okay, walk me through it.
In traditional smooth calculus, if you take a tiny microscopic step forward, let's call it Dix arc, and you square it, dx becomes unimaginably small. It becomes a second-order infinitesimal.
Right. It's so tiny that mathematicians just toss it in the garbage. It rounds down to 0.
Exactly. If you square 0.0001, you get 0.000001. It vanishes.
Yep.
But the microscopic step of Brownian motion, the W2 door, behaves entirely differently. Because the path is infinitely spiky, the spatial distance it travels up and down is massive compared to a smooth, straight line. The path is frantically vibrating.
So it's covering a lot of ground up and down.
A ton of ground. Now, the noise itself, whether the next tick is up or down, remains completely unpredictable.
So we still don't know the direction.
We never know the direction.
Yeah.
But we aren't looking at the direction. We are looking at the variance. We're looking at the squared magnitude of those swings.
Okay.
Imagine flipping a coin. One flip is random. But if you flip it 1 billion times, the ratio of heads to tails becomes incredibly predictable. Now apply that to our continuous timeline. Because we are dealing with continuous time, any interval, even a single second, contains an infinite number of microscopic random jumps.
Because it's continuous. So as we shrink our time steps down closer and closer to 0, we are cramming an infinite number of these tiny violent zigzags into the observation window.
Yes. And according to the law of large numbers, when you sum up an infinite number of these squared random microscopic jumps, the positive and negative uncertainties perfectly cancel each other out.
Wow.
The randomness collapses under its own infinite weight. The variance of the path converges with absolute mathematical certainty to its expected value. And the expected value of the variance of Brownian motion is exactly equal to the length of the time interval.
That is just, wow.
As one of our sources so poetically puts it, randomness dies and becomes time.
Randomness dies becomes time. Let me just make sure I'm internalizing the mechanics of this. In the traditional smooth world, the second-order variations, the squares are so small they get thrown away.
Right.
But in the stochastic, jagged world, the second-order variations are so violent and so aggressive that they refuse to be ignored. They force their way into the equation.
They don't just force their way in, they get promoted. The second-order randomness is so massive it gets promoted to first-order certainty. It becomes a deterministic flow equivalent to time itself.
That is staggering to think about. Over a long enough timeline, with an infinite volume of tiny chaotic events, the sheer mass of the chaos creates its own predictable clock.
Brilliance.
And this breakthrough leads to what the texts call Ito's multiplication table, which is basically the operational rule book for this new reality.
Right, the new rules of calculus.
It goes like this. If you multiply a microscopic time step by another time step d time times dt2, it equals 0. It's too small, it vanishes.
Yeah.
If you multiply a time step by a random step times dwt, that also equals 0.
Exactly.
But if you multiply a random step by a random step dwt 2 time, it survives. It locks in as dt2.
And that single substitution is the engine inside the Black-Scholes model.
Okay.
Without dwt222 equals dtt, we could not price derivatives. It just wouldn't work.
So let's look at what happens when we actually turn that engine on. Let's apply Ito's calculus to our perfect model, geometric Brownian motion.
Do it.
When mathematicians used this new rule book to transition from looking at absolute prices to looking at the continuously compounded growth rate, the log returns, a brand new, highly suspicious term, spontaneously appeared in the final equation.
It does pop right out, doesn't it?
It really does. The term is minus 1/2 sigma squared dt dollars, or frac 1/2 sigma 2 dt t-ball. Where did this negative fraction come from? Because it certainly wasn't in the original setup.
It emerges directly from the mechanical application of Ito's lemma. Specifically, when you are transforming the equation to look at log returns, you have to take the natural logarithm of the price.
Okay.
And to do calculus on a complex function like a natural logarithm, you have to use a mathematical tool called a Taylor series expansion.
Okay, hold on a second. For those of us who haven't sat in a university calculus lecture in a decade, what exactly is a Taylor series expansion and why are we expanding anything?
Fair question. Think of it like trying to draw a perfect complex curve, like a sine wave or a logarithm, but the only tool you have in your pencil box is straight lines and simple parabolas.
Sounds difficult.
A Taylor series is a way of approximating a highly complex curve by adding up a series of simpler polynomials. You start with a flat line, then add a tilted line to match the slope, then add a curved parabola to match the bend, and so on.
Right.
Each new term you add the first derivative, the second derivative, the third derivative, makes your approximation hug the real curve more tightly.
It's kind of like rendering a circle on an old video game console. You start with an octagon, and then you add more and more straight edges until it looks perfectly round.
That is an excellent way to visualize it. Now, in classical Newton calculus, when you use a Taylor series, you only need the first derivative. You just need the first straight edge. Because, as we discussed, the second derivative, the squared terms, shrink to 0 and disappear.
Right, they get tossed in the garbage.
But because we are using Ito calculus, where dwgt2 stubbornly survives and turns into needlelords, we cannot throw away the second derivative of the Taylor series. We are mathematically forced to keep it.
Oh, I see.
And the second derivative of a natural logarithm function happens to be -1 over x squared. When you multiply that through the formula, you get exactly day sigma 2 dtt.
Okay, so the math demands that this negative term exists, but what does it actually represent in the physical world of finance?
In quantitative finance, this term is known as volatility drag, or sometimes the volatility penalty.
Volatility penalty.
Yeah, it represents the friction of chaos. It means that because of the extreme, jagged violence of the asset's path, the sheer chaos of the dwt22 term, the actual realized long-term compounded growth rate of the asset is strictly and mathematically less than its average daily expected return.
Wait, let me make sure I'm fully grasping the real-world implication here. If the Taylor series is just a mathematical tool for estimating a curve, why are we suddenly treating this second derivative estimation artifact as a concrete financial penalty that actively eats my money?
Because it's real.
That sounds like a mathematical abstraction leaking into my actual wallet.
I know, but the mathematical abstraction perfectly mirrors the geometric reality of percentage losses. Ito's calculus mathematically formalizes a brutal truth of personal investing.
Okay, give me an example.
Let's pull this completely out of the theoretical clouds and look at your retirement account. Imagine you have a choice between two portfolios.
All right, I'm listening.
Portfolio A is a boring, massive S&P 500 index fund. It goes up a little bit most days, goes down a little bit on others. It is very stable.
Classic.
Portfolio B is a highly speculative, concentrated basket of emerging crypto tokens. It skyrockets 20% one day, crashes 15% the next. It is a violent roller coaster.
Okay.
Now, on paper, let's assume both portfolios boast the exact same average daily return of 0.05%.
So over a year, the arithmetic average of all their daily gains and losses is identical. A naive investor would look at that and assume both portfolios will end up with the exact same amount of money after 10 years.
Exactly. But they won't, because Portfolio B has a massively higher sigma, a much higher volatility multiplier. That volatility drag term, the track 122, is going to be huge.
Because the math is literally taxing the crypto portfolio for being chaotic.
The math is revealing the geometric tax of percentages. Think about a massive downward swing. If your crypto portfolio drops by 50% on Tuesday, you are left with half your money.
Right.
To get back to where you started on Wednesday, you don't need a 50% gain. You need a 100% gain.
Oh, man. That's true.
The math of percentages inherently punishes downward volatility. It acts as a massive anchor on compounding wealth. The fractal 1 2 sigma 2 is the exact quantifiable measurement of that anchor.
So the math actually proves that a boring, steady ride makes you tangibly richer than a wild roller coaster, even if the average speeds look identical on paper.
100%.
The wilder the ride, the more of your wealth is literally burned as friction just trying to navigate the jagged path. That isn't just theory. That completely changes how someone should structure their 401k.
It is the mathematical proof of why diversification and low volatility are paramount for long-term compounding. You want to minimize the sigma to minimize the drag.
All right, let's scale this up a bit. We've mapped out the exact cost of chaos on a single asset. We know what a single, jagged, volatile path looks like. But if you are a Wall Street quantitative firm, you aren't just looking at one path.
No, you're looking at thousands.
Right, thousands of interconnected assets globally. So how do mathematicians zoom out from tracking one single jagged line to seeing the whole board?
That's a great question.
In our sources, this transition is framed as the difference between stochastic differential equations, or SDEs, and partial differential equations, or PDEs. What is the difference between these two acronyms?
They basically represent two fundamentally different perspectives on the same dynamic system. They're two sides of the same coin.
Okay.
An SDE, a stochastic differential equation like the geometric Brownian motion we've been discussing, is a microscopic perspective. It is driven by d2d-dal, which is time, and d2t-do, which is our random, unpredictable noise.
Right.
When you solve an SDE, the answer you get isn't a single clean number. The solution is a simulation of countless, jagged, completely unpredictable paths. It's a Monte Carlo simulation of every possible crazy way the stock could move over the next month.
I actually found an analogy for this in the prep that really helped me visualize it.
Hey, let's hear it.
An SDE is like trying to understand the temperature of a boiling pot of water by tracking one single specific water molecule. You put a microscopic tracker on it and watch it bounce randomly.
I like this.
It zips left, gets violently knocked right, shoots up to the surface, gets dragged back down by a convection current. You are following the chaotic journey of the individual particle. In physics, they call this the Lagrangian view.
That's a really great visualization. The SDE is tracking the microscopic chaos. But a PDE, a partial differential equation, takes a macroscopic view.
The Eulerian view.
Exactly. To use your analogy, a PDE is like stepping back from the stoves, ignoring the individual molecules completely, and just looking at the entire boiling pot from the outside. You measure the overall temperature gradients, the pressure distribution, the average heat transfer. You are mapping the environment, not the particles.
And notice what's missing in the Eulerian view. When I look at the equations for PDEs in the texts, specifically the famous Black-Scholes equation used for pricing options, the random noise term is gone.
Completely gone.
There is no WD anywhere to be found.
Exactly. PDEs do not contain explicit random noise. The randomness of the billions of molecules has been absorbed into the aggregate. Instead of jagged paths, PDEs use smooth, partial derivatives to constrain the system based on boundary conditions, producing a deterministic, smooth probability surface.
So the SDE gives you a messy ball of yarn?
And the PDE gives you a sleek, curved sheet of expected values.
But if one is a chaotic mess of infinite yarn and the other is a perfectly smooth sheet of metal, how do we bridge them? They seem irreconcilable. How do mathematicians translate the micro chaos into the macro certainty?
That translation is arguably the most profound mathematical theorem in quantitative finance. It is called the Feynman-Cach formula.
Feynman, as in Richard Feynman, the famous quantum physicist with the bongos.
The very same. He developed it in the 1940s while working on quantum mechanics, and Mark Cach independently formulated aspects of it shortly after.
What does it do?
The Feynman-Cach formula mathematically proves a stunning equivalence. It proves that solving a macroscopic deterministic PDE is exactly equal to taking the expected average value of an SDE's infinite random microscopic paths.
Wait, let me stop you there and make sure I'm wrapping my head around the scale of that statement.
It's massive.
You're saying if I program a supercomputer to simulate a billion different random, jagged, volatile paths of Apple stock using an SDE, and then I calculate the exact average of where all 1 billion of those squiggly lines end up, that final average number will perfectly, flawlessly match the answer I get by solving a smooth, non-random PDE on a single sheet of paper.
Yes. The expected value of the microscopic chaos flawlessly equals the macroscopic deterministic certainty. It's beautiful.
That is unbelievable.
But what is truly fascinating is how this theorem is applied in Wall Street trading. It is more than just a neat mathematical trick to save supercomputer processing time. It is the core philosophy of how derivative pricing works in reality.
How so? Like on the trading floor?
Think about what a market maker does at an investment bank. A market maker sells you a call option on Apple stock. By selling that option, they are now exposed to the random, chaotic movements of Apple's stock price.
Right. They took on the risk.
And they hate chaos. They want to lock in a risk-free profit. So they immediately create a hedging portfolio.
They buy and sell shares of the underlying Apple stock to offset the risk of the option they just sold you.
Precisely. They calculate a very specific ratio known as the delta, and they continuously buy and sell tiny amounts of the stock as the price moves. This hedging portfolio is designed to perfectly mathematically oppose the random movements of the option.
Okay, so if the option loses value due to a random downtick, the hedging portfolio gains the exact same amount of value.
Exactly.
So they are actively, manually trying to cancel out the chaos of the market.
And by doing this, they're physically acting out the math. By perfectly opposing the random noise, the market makers are forcing the bracket in the mathematical equation that contains the randomness, the dx or du term, to sum to zero.
Wow.
By executing this math in the real world, through active, frenetic, millisecond by millisecond trading, human beings literally kill the random term in the SDE.
They don't just calculate the math, they execute the math into existence. That is incredible.
Yes. When the hedging portfolio is continuously rebalanced, the SDE sheds its randomness entirely. The unpredictability is neutralized by human intervention, and the equation collapses directly into the deterministic Black-Scholes PDE.
So the Black-Scholes equation isn't just an abstract law of nature like gravity, passively describing how options behave.
Not at all.
It is a strong-arm intervention. It works because human traders are actively suffocating the Brownian noise, extracting a single sliver of absolute risk-free certainty out of a fundamentally unpredictable universe.
That is a perfect way to phrase it.
That honestly shifts my entire perspective on what mathematical finance actually is. The map only works because thousands of human traders act as an army, standing guard, constantly hedging, forcing reality to submit to the equation. They build the mathematical cage, and then they stand at the bars to make sure the beast doesn't get out.
That's exactly what's happening.
All right, I want to dig into a very specific, highly technical trick revealed deep in the sources that mathematicians use to actually solve these complex equations on paper.
Oh, a log transform.
Yeah. When trying to solve for the future price of a stock, $s using geometric Brownian motion, you can't just integrate the equation directly. Instead, mathematicians temporarily invent a completely fake dummy variable.
They do.
They decide, out of thin air, to let Vivalite equal the natural log of 7SES. When I saw this, I was baffled. If the goal is to know the future stock price, why on earth do we invent a fake variable, run it through all this complex Ito calculus, and then try to work backward? Why not just integrate the original stock price equation straight down the middle and be done with it?
It's an excellent question, and it highlights a major frustrating roadblock in stochastic calculus known as the variable entanglement problem.
Variable entanglement.
Let's visualize the geometric Brownian motion equation one more time. DCA, A E ski A dt plus sigma 6T2, ATTT plus sigma tan dw2. In order to integrate a differential equation cleanly, you usually need to isolate the variable you are solving for.
Right.
But look at the equation. The change in price, C-tose is on the left, but the current price is hopelessly stuck on the right side, multiplying both the time step d-bros and the random noise.
Ah, I see. The rate of change relies on the current state, but the current state is constantly shifting because it's being bombarded by noise. They're braided together.
They are completely tangled. You cannot separate the SIGRI away from the W-Dober dollar to perform a standard integration. It is mathematically blocked.
So how do they get around it?
Well, mathematicians discovered a loophole. By inventing this dummy variable, the ln-SRE, and running that log transform through Ito's lemma, something deeply magical happens to the algebra.
The natural log acts like a solvent on the entanglement.
Exactly. When you apply Ito's lemma to the natural log of SIGRI, the dollar term entirely cancels out of the numerator and the denominator. The variables cleanly, perfectly separate. The messy coefficients that were trapped next to the noise, the nu and the sigma and the SIGRI, magically collapse into pure, standalone constants.
And once you only have constants sitting next to your dollar and dilute, the calculus becomes easy.
Integration becomes trivial at that point. You simply integrate the constants over the time period, t dollars. You arrive at a clean solution for your dummy variable, $50.
But of course you don't care about follows, you want the actual stock price.
Right, so as the final step, you simply exponentiate the entire result. You reverse the natural log operation to snap back out of the dummy dimension and arrive at the real future stock price, $6.
So the log transform isn't altering the fundamental reality of the stock. It is a mathematical smokescreen.
Pretty much.
It's like realizing a mountain is too steep to climb, so instead of trying to scale it, you dig a tunnel through a different spatial dimension underneath the mountain. When you pop out on the other side, you are exactly where you needed to be, but the journey was 1,000 times easier.
It is an elegant bypass around an otherwise impossible integral. It proves that sometimes the best way to solve a complex problem is to map it into a different domain where the rules are friendlier, solve it there, and then translate the answer back.
We are nearing the end of our whiteboard here. We've gone from the staggering botanist pollen grain to the volatility tax that eats your retirement, to the army of market makers strong-arming chaos into a PDE, to tunneling through mathematical dimensions with log transforms.
It's a lot to take in.
It is. But before we finish, there is a crucial boundary condition we absolutely have to discuss. It's the boundary where mathematical theory crashes into the messy reality of human markets.
Ah, yes, the discrete boundary.
Right. In the sources, there is a prominent warning about a common trap that graduate students, and honestly, even some quantitative professionals fall into. It's the assumption that the random noise step, AXL, is absolutely equal to the square root of the time step.
It's a very common mistake.
Why is assuming 8x score so dangerously wrong?
It is a subtle error, but if you build a trading algorithm on it, it will literally blow up your fund.
Yeah.
Mathematically, 8x6 does not equal way. The proper complete formulation is AEDX, whereas a standard normal random variable.
Okay, Zeller times the square root of time. What is the fundamental difference in purpose between the Zeller and the Sal? Why do we need both?
Think of the Zellers as the soul of the randomness. The Zeller is the actual dice roll. It is a standard normal variable, meaning it dictates the unpredictable direction. Does the stop jump up or does it jump down? Is a positive one or a negative one? The zero provides the pure, unadulterated uncertainty.
And the square root of time.
The squared, on the other hand, is just the body. It represents the scale. It dictates the physical limit of how large that random jump can mathematically be over that specific microscopic time interval.
So if a student just writes DSE at GDAL, what are they accidentally doing?
By dropping the Zelio, they are stripping away the soul of the model. They are removing the dice roll entirely. They are taking a process that is supposed to be stochastic, unpredictable, and chaotic, and turning it into a completely deterministic, rigidly predictable clock.
Oh, wow.
Yeah, they are saying, I know exactly how much the stock will move, and I know it will always be positive. You destroy the very essence of the stochastic model.
You're trying to model a casino, but you took away all the dice.
Exactly.
And this fundamental misunderstanding brings us back to the most important rule we learned today. Ito's magic axiom, dWTT2 equals dP2. The idea that chaos squared perfectly equals the deterministic flow of time. That rule is the linchpin holding the entire Black-Scholes derivative market together.
It is.
But there is a massive catch to that rule, isn't there?
The biggest catch in modern finance. That magic rule where the violent variance of the market perfectly, neatly collapses into the predictable certainty of time, it only exists in the absolute vacuum of continuous time.
Let's define that vacuum. Continuous time means what exactly?
It relies on taking the mathematical limit as the time step, D2 approaches zero. It assumes we were observing the market and trading in the market in infinitely small microscopic slices. It assumes time flows like a perfectly smooth, unbroken river.
But the New York Stock Exchange does not flow like an unbroken river. Reality is not a mathematical vacuum.
Precisely. Reality is fractured. If you zoom out from the continuous mathematical vacuum to discrete, real-world time steps like checking a price every 1 second, or every 1 hour, or overnight when the market is closed, that magic rule shatters.
Because it's no longer continuous.
Right. The time step is no longer approaching zero. It is a fixed, discrete chunk. And when the time step is fixed, the squared noise, DWT22, does not neatly collapse into a constant dB dollar. Instead, it transforms into what statisticians call a chi-square distribution.
A chi-square distribution. I want to make sure I understand the mechanism of that. If I square a normal bell curve of random possibilities, what happens to the shape of it?
Well, when you square a standard normal distribution which is symmetrical with both positive and negative possibilities, all the negative numbers become positive. So you effectively fold the left side of the bell curve over onto the right side.
Okay.
You create a new skewed distribution that is strictly positive, but here is the critical part. It still has variance. It is still a distribution of probabilities.
So it regains its uncertainty.
It absolutely regains its uncertainty. The randomness refuses to die. Because you aren't trading infinitely fast, the variance doesn't collapse into a predictable clock. It stays random.
And I imagine this introduces massive structural errors when banks try to apply continuous mathematics to a discrete reality.
Massive. In the trading world, this gap between theory and reality is known as gamma replication risk.
Gamma replication risk. How does that manifest in the real world when things go wrong?
Remember our market makers who are manually hedging to kill the noise and force the Black-Scholes PDE to work.
Yeah.
That hedging only perfectly neutralizes the risk if they can trade continuously, infinitely fast as the price moves. But in the real world, the market can gap. Imagine a stock closes at $100 on Friday. Over the weekend, terrible news breaks. On Monday morning, the stock opens at $50.
Wow.
It didn't trade at 99 or 80 or 60. It teleported from 100 to 50.
The continuous river broke into two separate ponds.
Exactly. The time step was the entire weekend. It was highly discrete. The market maker couldn't dynamically adjust their hedge on the way down. The continuous math assumed they could, but reality prevented it. When the market opened, their hedge was completely wrong, their protection evaporated, and they suffered catastrophic losses.
Like the 1987 Black Monday crash, portfolio insurance algorithms assumed they could continuously sell into a falling market to protect their positions. But everyone tried to sell at once, the liquidity vanished, the continuous time assumption broke, and the market violently gapped down.
That's exactly what happened.
The math told them they were safe, but the math was operating in a theoretical universe that the actual stock market suddenly decided not to inhabit.
Exactly. Or look at the collapse of long-term capital management in 1998. The smartest mathematical minds in the world, including Scholes and Merton themselves, built highly leveraged portfolios based on continuous time convergence. But when the Russian debt default hit, markets fractured. The continuous curves became jagged, discrete cliffs. The chi-square uncertainty reared its head, the variance exploded, and the fund collapsed, nearly taking the global financial system with it.
Wow. Okay, let's step back and look at the whole whiteboard one last time.
Yeah.
We have been on an incredible, deeply complex journey today.
Taking a long one.
We started with a staggering drunkard in an empty field, simple Brownian motion, pure, unbiased noise. We put them on a moving walkway with arithmetic Brownian motion, but realized that model generated impossible negative stock prices and ignored the reality of proportional wealth destruction.
Right.
So mathematicians built the perfect cage, geometric Brownian motion. A model that mathematically respects zero, scales perfectly with percentages, and operates without memory or calendar constraints.
A true theoretical masterpiece.
But to unlock this cage, we had to invent a completely new branch of human knowledge, Ito's calculus, where chaos squared equals time. That new math revealed the hidden cost of chaos, the volatility drag that mathematically penalizes volatile portfolios.
Yeah.
We looked at the Lagrangian view of individual chaotic particles in SDEs and the Eulerian view of smooth macro probability surfaces in PDEs. And we witnessed the ultimate bridge, how the Feynman-Cox formula allows human market makers to actively strong-arm the chaos into the absolute certainty of the Black-Scholes equation.
It is, without a doubt, a masterpiece of human ingenuity. It is arguably the most successful application of theoretical physics and mathematics to human behavior in history.
It truly is. It represents the triumph of quantitative finance, the audacity to map the unmappable and put a price tag on the unknown.
Absolutely.
But we want to leave you, the listener, with a final provocative thought to mull over as you digest all of this. Everything we just unpacked, our entire modern financial pricing framework, the Black-Scholes model, the trillions upon trillions of dollars trading right now in the global derivatives market, it all balances on a single fragile assumption.
It really does.
It relies on the mathematical assumption of continuous time. It assumes that time is a liquid river. It assumes that algorithms and traders can buy and sell infinitely fast with zero friction, allowing the wild, violent variance of the market to smoothly and safely collapse into predictable time, where a diddle squared safely equals DD true.
But human markets are not a liquid river.
No, they aren't. They are fundamentally discrete. They have ticks, they have circuit breakers and trading halts, they have weekends and overnight gaps where wars start, pandemics break out, and CEOs resign, but no one can trade.
Exactly.
If the mathematics keeping our financial system afloat demands infinite continuity to keep the cage locked, but reality is fundamentally fractured, chunky, and discrete. Are our flawless financial models actually caging a beast that will eventually, inevitably, break out?
It makes you wonder.
It does. When you look at flash crashes, black swan events, and the overnight evaporation of liquidity, you really have to wonder. We built the most beautiful mathematical cage in human history, but maybe the cage isn't as solid as the whiteboard makes it seem?